All right, in section 5, we're going to look at complex fractions and how we can simplify complex fractions. So a complex fraction is generally just going to be a fraction with another fraction or a couple different fractions. So a fraction in the numerator and denominator. So we have fractions over fractions, and that's what makes a complex fraction. So, for example, I could have 3/4 divided by 1/2, and we could just use some rules of fractions to clear that up. Now, there are two methods that we typically can do, because one, we can use the fact that a big fraction bar like this really means division. So we could talk about the fact that this is just 3/4 divided by 1/2, and then we could do our normal operations on fractions. Multiply by the reciprocal, factor, and cancel out. The other way we can do it is we can actually multiply by what's called the LCD. So we'll call this method 1 and method 2. So method 1, we are simply going to add or subtract the numerator and denominator separately, or top and bottom separately, and then divide. So this is going to involve getting common denominators with your adding the numerators over your common denominator, and then doing the division. So if we look at this first problem, m cubed over 3n divided by negative m to the 4th over 9n squared. The good news is this already has a single fraction over a single fraction. So we can go ahead and directly just go ahead and turn that to a division problem. So this is m cubed over 3n divided by negative m4 over 9n squared. And the nice thing about divisions of fractions, remember, from elementary school, you can take your first fraction, change this to multiplication, and then take the reciprocal of your second fraction. So you're turning it into multiplication. And then multiplying rationals, you can multiply straight across, you can cancel up and down or diagonal. So what I see here is I have 3 m's here and 4 here, so I can basically cross out 3 of the m's and be left with 1 on the bottom. I can cross out 1 of the n's here, and I'm just left with 1 n on the top. And then I have 9 over 3, which simply reduces to 3. So now if I see what I have left on the top, I just have a 3 and an n, and on the bottom I just have a negative m. So those two fractions, that complex fraction reduces just this one simpler fraction. Okay, let's look at another one over here. Now this one, we also have everything added together. Even though there's a plus sign, it's already a single rational expression. So it's already 1 over 1. So we can turn this to m plus 5, or m plus n over 5, divided by m squared minus n squared over 5. And then when we do the reciprocal, you'll see some things will cancel out. We have m plus n over 5 times 5 over m squared minus n squared. So right away I see the 5's go away, but there's actually more that can be done, because remember, in any rational expression, it's always nice to factor the denominator. So this will be 1 because we essentially canceled it out. And this is the difference of two squares. So we have m minus n, m plus n. And now I can cancel diagonally and get rid of this m plus n. So now on the top there's nothing left, so if there's nothing left, we always put a 1 over m minus n. So we have some other ones here, you see, where we have a fraction over fraction. Here we have a fraction over a sum of fractions, and we have a bunch of fractions. So just a bunch of different kinds of problems. So let's look at this first one here. Again, this is a single fraction over a single fraction to start with. So I can actually rewrite that 5x squared minus 5x minus 30 over 45 minus 15x divided by the bottom fraction, which is 6 plus x minus x squared over 4x minus 12. Now, I know I'm going to turn to multiplication and flip it, but I can try to factor these as I go. For example, I know the first one I can take out a 5. So that's going to be 5x squared minus x minus 6. I can take a 15 out of this one and be left with 3 minus x. Multiply, now the 4x minus 12 is going to go to the top, and this is going to go to the bottom. So if I take out a 4, I'm left with x minus 3. And now I could try to unfoil it. The one problem is you notice that this has the negative sign in front of the x squared. So what I would probably do is I would probably factor out a negative 1 to make that positive x squared minus x and then minus 6. So when you're trying to unfoil, when you're trying to factor, it's always good to have that first number by itself. So now you can see that we have some stuff that will cancel. And I could factor this and this further, but if you notice, they're the same trinomial. So I might as well just go ahead and cross that out. 5 over 15 over here on the left can reduce. 5 over 15 will leave me a 3 in the bottom. Now I have 4 and 3. That doesn't work. I have x minus 3 and 3 minus x. Now those are close to being the same, this guy and this guy. But you'll notice they're reversed in subtraction. So if you cancel things out that are reversed in subtraction, you're going to be left with a negative 1. So on the top, I'll have 4 times negative 1, because that is multiplied. So I'll have negative 4. And on the bottom, I'll have 3 times negative 1, which is negative 3. So this is just 4/3. So that huge mess of a complex fraction simplified to just a regular old rational number of 4/3. So let's look at this one. Now this one's a little trickier because you have this numerator, and the numerator is one fraction over one denominator, but this bottom one is not. So to add those together, we will have to get the same denominator. So we have a and b. So the common denominator is obviously going to be ab. So what I'm going to need to do is we need to get an a down there and a b down here. So to add fractions and rational expressions, you have to have the same bottom. Well, of course, if I multiply it on the bottom, I have to multiply it on the top as well. So I'll do a over a there, and I'll do b over b here. So this one's now going to simplify, so we'll have a squared minus b squared over ab, and then divided by a minus b over ab, because you have the common denominator of ab, and you're just subtracting the numerators. So now I can rewrite this as my division problem, a squared minus b squared over ab, divided by a minus b over ab. Now again, same thing with the division. We will flip it. I'm going to go ahead and factor this. So we have a minus b, a plus b, all over ab. And now it's going to be times ab on the top and a minus b on the bottom. And then obviously you can see some things cancel. The ab's cancel, because remember, you can cancel up and down and diagonal. And the a minus b's cancel. So I'm just left with a plus b. So this one down here is very similar. We have two fractions on top and bottom. So again, the problem with this one, you don't have one fraction, you have two on top, two on bottom. So what we're going to have to do is we're going to have to get common denominators of the top and bottom. And it's relatively simple, so we'll just have an x minus 3 on the bottom here. And then of course I'll have to add it to the top as well. Down here I'll put an x minus 3 on the bottom and an x minus 3 on top. So what that's going to give us, I'm going to put the 5 in top because we're going to multiply it to the x minus 3. Minus 2 over x minus 3. Because again, I have these same denominators now. That's why I multiplied the x minus 3 on top. Over 4 times x minus 3 minus 1 all over x minus 3. So now we have one fraction on top and bottom, one rational expression that we can simplify. So we get 5x minus 15 minus 2 over x minus 3 all over 4x minus 12 minus 1 over x minus 3. So now it's 5x minus 17, because we got the negative 15 and the negative 2, over x minus 3, all over 4x minus 13 over x minus 3. Well, so now again, now we have it as a single rational expression because we added those those rational expressions together with the common denominators. So now we'll get 5x minus 17 over x minus 3. I know it's going to be divided by the bottom one. If I want to go ahead and make the jump and say, well, I know it's going to be multiplied by the reciprocal, I certainly can. Be careful doing that, but you can. The only thing I see cross out is the x minus 3. So I'm going to be left with 5x minus 17 over 4x minus 13. The last one we'll look at with method 1 is this guy. It's got 3 denominators. It's got y squared, xy, x squared, and then x squared, xy, y squared. Now, if we think about the LCD of both is going to be x squared and y squared. And the reason being, this is the smallest expression that will divide all 3 terms. So what I'll need to do is, for this one, I'll need to add an x squared on top and bottom. This one has an x and a y, so I'm going to need another x and another y. So I'll add xy there. And the last one, I'm going to need to put a y squared. So if I rewrite this, it's going to be 2x squared minus 5xy minus 12y squared, all over x squared, y squared. Now for the denominator, you're going to have the same LCD. That does not have to happen. You can have different LCDs. In this case, we get the same one. So we'll do y squared, y squared. We'll need another x and another y, so xy. And here we need the x squared, so I'll put an x squared. So this one's going to turn out to be 2y squared plus xy minus 3x squared, all over x squared, y squared. Now I can go ahead and try to factor this by whatever method you want. It's got the leading coefficient not 1, so you can do your box method or your split the middle method. Whatever method you feel comfortable factoring with is fine. But this is going to factor as 2x and x. And then since we want negative 5 in the middle, I'll put negative 4 here and plus 3 here, because when I FOIL, I'll get the negative 8 and the plus 3, which is my 5, negative 5, which I want. And since it has x and y, I put the x, so to make it with the y, you just tack a y on the end here. That's all you have to do. Over x squared, y squared. And then I'm going to multiply by the reciprocal, which is going to be x squared, y squared. And then I'll factor this polynomial here. Now this one starts with y, so we'll start with 2y and y. And this one's going to factor as we need 3 in the middle, so we'll put, or 1 in the middle, pardon me, so we'll put plus 3 minus 1, because that gives us our 3 minus 2, which is positive 1. And then we'll just put an x on each of these, because that's the second variable. Now the cool thing is these cross out, the x squared, y squared, and nothing else really does. You might be tempted to factor cancel this and this out, but if you notice, the variables are on different things in that polynomial. So our final answer is simply going to be 2x plus 3y over x minus 4y over 2y plus 3x times y minus x. So the way we've done the complex fractions work for every complex fraction. There is a slightly different way that we can do it, and we'll call this method 2. And the way this works is you can really do the whole problem at once instead of doing the top first and then the bottom and then putting them together. You can actually do it all at once. And the way we do this method 2 is we're simply going to multiply each term by the LCD of all the terms. So if we look at all the terms on top and bottom, there is a super LCD, mind you, where it's the LCD of all the terms. And if we multiply everything by that, a lot of cool things will cancel out. So this is good when you have more complex problems and you have lots of things going on. So if I look at this one, we have three denominators. We have a denominator here, here, and here. So the LCD of those three is simply x and y. So the cool thing is if I multiply everything by that LCD, so xy here, and xy here, and xy here, I multiply it to the tops of all those things, because when you multiply something, it's multiplied always to the top. Lots of stuff will cancel. The x's cancel here, the y's cancel here, and the xy's cancel here. So all I'd be left with is y plus x over 2. So that is a super efficient way to do the problem. It is a little unnatural. It's more natural to do method 1 where you're adding things together and then dividing. But if you multiply by this LCD, it will clear them very quickly. If we look at this one, now if I look at the LCD here, I do see one problem, and that problem comes in this, because that is not factored yet. So to make my LCD a little easier, I'm going to make sure I factor all the denominators. Top is no problem, but this bottom is the difference of squares, so it's actually x minus 1, x plus 1. So now when I'm looking at all the denominators, my LCD is going to be a little more complicated. My LCD is going to be x minus 1, x plus 1, obviously, because of the bottom. If I look at this guy here, it's an x plus 1, but I already have that in my LCD. The one thing I'm missing is an x. Even though both terms have an x, the x by itself is an independent term. So now I'm going to take this LCD and I'm going to multiply it to my whole complex fraction, always on the top. So I'll just write it here again, and then we'll put the LCD in and we'll start canceling things out. So my LCD is x, x minus 1, x plus 1. Again on the top, and it's times 1, so it's just that. X, x plus 1, x minus 1, x, x minus 1, x plus 1. So hopefully lots of good things cancel. They do. We get x's that cancel here, x plus 1's that cancel here, both an x minus 1 and an x plus 1 here. Let's go ahead and see where we're at. We have x minus 1, x plus 1, minus x times x minus 1. And on the bottom, I just have x. So that's always nice. So I'll go ahead and I'll FOIL and distribute the top, clean that up a little bit. So if I FOIL these two, I know that's x squared minus 1 because I unfoiled it and got that. Here I can distribute the negative x. So that's minus x squared. And that's going to be a negative x. So negative x, or positive x, because a negative times a negative is positive, all over x. Now you can see on the top the x squareds go away, so I'm left with negative 1 plus x over x, which would be our answer. I mean, if you wanted to, you could write it as x minus 1 over x. That would also be fine, but that's what your final answer would be. All right, let's look at one more using this method. So the last one we're going to do is somewhere down here. So if I look at the LCD of this, now we have three denominators. We have this one, the other ones are 1. We actually have 5 denominators, but these are really the ones I have to look at. And the LCD of n and n squared is always the highest power, so that would just be n squared. So I'm going to multiply everything by n squared. Even the things that don't have denominators, I still have to multiply by to make this work. And then a bunch of stuff will cancel, n squared here. We have one n that will cancel here and both n's here. So that's going to simplify to n squared minus 4 over n squared minus n minus 6. So now we have a polynomial rational expression that can be factored. This is n minus 2, n plus 2. Bottom two numbers that multiply to negative 6 add to negative 1 are n minus 3, n plus 2, which quite conveniently now you see will cancel out. So I'm simply left with n minus 2 over n minus 3. So doing the multiply everything by the LCD is a really quick method. You do have to be careful because obviously there's a lot of things going on at once. but a really neat way to simplify these expressions that do come up quite a bit in mathematics.